The reason that mathematicians love math is because there's this handful of principles that govern everything. And once you wrap your mind around that handful of principles, no problem is impossible, and you see the world in new ways. You're able to get new information, new relationships about things that you encounter all the time. So what are those principles? Well, what is addition? And I can't say that addition is adding. I'm going to say that addition is when I put things together. So, and do not say putting numbers together. Numbers are adjectives. I can't put adjectives together. I can put nouns together, put things together. What is subtraction? And subtraction could be two things. It could be take away, but it could also be, and big or here, or I could compare things. So just a quick example, suppose that there are 10 dogs in a kennel and 3 are adopted. Well, then I'm taking 3 dogs from 10 dogs, leaving 7 dogs. But what if now I compare and there are 7 dogs in the kennel, but only 3 cats? Are there more dogs or cats? When I compare, I don't have to have like type objects. When I take away, I do. So in the previous example, 7 dogs compared to 3 cats, there's 4 more dogs. That's a subtraction, but you didn't take anything away. Think about the problem. I have $20, you have $15. Who has more? Did I take $15 away from you, or did you take $15 away from me to find the difference of 5? So next comes multiplication. Multiplication is simply repeated groups. So there's some kind of a group, and there's some kind of a operator on that group that causes repetition. So if I see 3 times 5, that literally means 3 groups of 5. So division is a regrouping. So a quick example of a regrouping, suppose I have 8 objects and I want to split it into 2 groups. Well, that's 8 divided by 2 is equal to 4. So the 8 objects are all still there. It's just now that 8 objects have been put into 2 separate groups. And the 4 represents how many are each of these new subgroups. Next comes substitution. Substitution says that you can replace anything with its equal. Now, most of the time when we're in algebra, or any math class for that matter, we just do substitutions. And you're about to see that for the next many, many examples. So, all operations are binary. Binary, bi is 2, like bicycle, biplane, etc. Binary simply means that you can only combine 2 numbers at a time. You can't do more than 2 in one operation. And how do you decide which 2? Well, you use the order of operations. So looking at the order of operations, parentheses, exponents, multiplication, division, addition, subtraction, I see there's a multiplication here, a division here. Those are both done on the same line. You'll see why in just a moment. This becomes then 6 plus 3, which is 9. Now, literally what we're doing here is a substitution. We're replacing the 2 plus 3 with its equal 6. We're replacing 10 to 5. Well, isn't that interesting? We're replacing 10 divided by 5 with its equivalent 2. And then we're going to replace 6 plus 2 with its equivalent 8. Well, same over here. We'd see that there is a parenthetic here. This becomes then 2 times 5 squared plus 4. And notice again, we're simply replacing something with its equal. But how do we know? We can only do 2 numbers at a time. Next, I see exponents. So this becomes 2 times 25 plus 4. And again, I'm substituting equals for equals. Now I do multiplication, division. So 50 plus 4. And then ultimately, I get a final result of 54. But all of those are substitutions. That's why we don't call those evaluations. Evaluation refers to some kind of a variable expression, and then a specific value for that variable that I want to substitute and evaluate. So over here, I see that multiplication. So 18 plus 2 minus 20. Oh, a lot of times you don't realize that operations are binary, because at this point you may see this whole thing as being a 0. But did you realize that you saw, first of all, that it's 20 take away 20 before you saw that it was 0? So all operations are binary. Now, these are definitions. And the struggle that most people have in advanced mathematics is they're good with arithmetic, or good enough, but they struggle with definition. So there are several ways that you can deal with addition, subtraction. We'll talk about them a lot in class. But 7 take away 3 is 4, but 7 plus negative 3 is also 4. 4 take away 10 is negative 6, but 4 plus negative 10 is also negative 6. Negative 8 take away 2 is negative 10, but negative 8 plus negative 2 is also negative 10. Negative 5 subtract negative 5 is actually 10. 5 plus 5 is also 10. 12 subtract negative 3 is 15. So is 12 plus 3. And negative 20 take away negative 10 is actually negative 10, just like negative 20 plus 10 is negative 10. So subtraction is the same thing as addition of the opposite. So that's the strict definition. And that is defined mathematically that way. Now, sometimes what people do on a problem like this is they'll see a number line and they'll say, I'm going to start at 7 and I'm going to move backwards 3 units and see where I land. So the takeaway on a number line is typically to the left. But it won't work on this problem over here. That number line model will not work there. So you have to have a way to handle that troublesome little take away the negative. And what a lot of people do is every time they see a subtraction, they'll say, well, I'm going to change the subtraction to an addition and change the second number to its opposite. So it becomes then 7 plus negative 3. Now for this kind of a problem, I think of that as a cash debt model. I have $7 of cash, but I have $3 of debt. Am I still in the positives, or have I reached the negatives? Same way here on a number line model, I would think of starting at 10. I would think of starting at 4 and moving back to the left 10 units, and that would take me past 0. How far past 0? Well, 6 to the left. Over here, this is the cash debt. I have $4 of cash, but I have $10 of debt. So I'm in the hole $6. Over on the double operation, subtract negative, what a lot of people do is they simply say, I'll change the subtraction to a negative and change the sign of the number being taken away. And then it does become 5 plus 5. Same way here, that 12 take away negative 3 is like 12 plus 3. Negative 20 take away negative 10 is like negative 20 plus 10. Now, there's a shortcut for single-signed addition and subtraction. And that shortcut is like signs add, unlike signs subtract. So let's go back and look at these problems one more time and just look at what we're doing. I see a 7 and I see a 4. I think of the 7 as a positive, and I think of the 3 as a negative because of the subtraction sign. Same way here, I see the 7 as a positive and the 3 as a negative. So I'm going to take 3 from 7 and get 4, and then I ask myself the question, should it be positive or negative? Well, if there's more positive, the answer is positive, but if there's more negative, the answer is negative. So consider this problem down here. I see one positive and one negative. So a positive 4, a negative 10 because of this minus sign right here. So I'm going to subtract 4 from 10 is 6. But should it be positive 6 or negative 6? Well, I took more away than I had, so it should be negative. So that reasoning can work pretty good too. This next part assumes you're okay with fractions, but 10 divided by 2 is 5. I could call that not 10 times a half, but I could say half of 10 is 5. One and the same. 30 divided by 3 is 10. 30 times 1/3 is like saying 1/3 of 30, also 10. Division is the same as multiplying by the reciprocal, the flip of the fraction. So if I see this 2 as being a 2 over 1, then I flip it and it becomes 1/2. By the way, that is the rule that typically you learn when you're in elementary, junior high for the division of fractions rule. Some people say keep, change, flip. They keep the first number the same. They change the division to its reversing operation times, and then they flip. But that actually is the actual definition of division for all things, whether they're fractions or not. Division is the same thing as multiplying by the reciprocal. Now, these next few, you'll do so intuitively that you'll not even see the need for having a formal description of what's happening here. But the commutative property, commutative, is the idea that you can change order. It's the same root where we get the word commuter. You live in one place, but you change position to work. Maybe you live in Groom, but you work in Amarillo or Pantex or wherever. So it just says you can reorder a problem. A lot of you would see this in your mind as being 7 plus 3 plus 18. That would be the most efficient way to do it. And then you'd see this as becoming a 10 plus an 18 for a 28. Notice again a couple of different things that that I can only operate on two numbers at a time, but order doesn't matter for an addition problem. Now, order does matter for subtraction problems, and that's why it's important for me to see that this is the same problem as -4 plus 23 plus -6, which then allows me to rearrange it to become -6 plus -4 plus 23, which then simply becomes -10 plus 23 is equal to 13. Notice that we did a couple of different things. We had to rely on the fact that the definition of subtraction is addition of opposites, so that this then allows me to get to this problem here. I wouldn't write all those middle steps. Matter of fact, I wouldn't write anything except I would see -10 plus 23 is positive 13. You can also reorder multiplication problems, and the natural reordering that I'd see here, I don't know that I'd always write it, I'd just see it, would be that this becomes 2 times 5 times 38, which becomes 10 times 38, which becomes 380. And I do that with such fluency that you may not even be aware that you're doing a reordering and that you're only combining two numbers at a time. I could do the same trick right down here, and it would become 5 times a 2 times a 17 would become a 10 times a 17 would become a 170. And again, you do those things so intuitively you may not be aware of how important that principle is. So just as a note, the commutative property is what you do when you're doing something like 2x times 3x squared. What you're actually seeing is that that's a 2 times an x times a 3 times an x times yet another x, because x squared is 2 factors of x. And then you're rearranging that as a 2 times a 3 times an x times an x times an x, just a rearrangement. And then you're replacing 2 times 3 with its equivalent, 6, and you're replacing 3 factors of x with its defined exponential form, x to the third power. And if you're an experienced student, you'll do all of that in your head, but it's important for you to realize that there are a lot of principles being played out in that little short thing. So association means that I can only combine two numbers at a time, but which two? Well, I could do it this way, And I could call that 6 plus 7 is 13, and then 13 plus 8 becomes 21. Or I could associate it this way, and then it would become 6 plus 15, but notice again, it's still 21. I could do this one like this and call this 6 plus 13 is 19, plus another 7 is 26. Or I could do it this way and call that 6 plus 20, and call that one also 26. Again, that's something that you would do so quickly in your head, and you would never write those grouping symbols. But remember, that fundamental principle is that you can only combine two objects at a time. And you get to choose which object, and if it's strictly addition, then you can rearrange, you can group them in any manner you'd like. Just going strictly on this multiplication problem, I could see that as 6 times 4 is 24. Or I could see it as 2 times 12, also the 24. Over here, I could see this as a 20 times a 6, which is a 120. Or I could see it as a 4 times a 30, also a 120. So the association won't affect the outcome. And this is just like a chess move that you're putting in your toolkit. So when you look at complicated things, you'll have an idea of what your options are, and you'll choose the one that might be most effective for you. So there are 3 types of multiplication. Single thing is multiplied, order doesn't matter. So I'd take this order, and in my head I'd say 10 times 23 is 230. On this one, order doesn't matter, so I'd just take the natural order, but I'd replace the 2 times 3 with a 6, and then 6 times x is simply 6x. Just to note, this multiplication sign here is called explicit. It's expressed. But over here, let's T, over here, this is called implicit or implied multiplication. And E-I-M-P, oh, that's a P. Implicit multiplication, but it's still just 6 times x. Over here, this is like the example I showed you a moment ago. In your head, you're actually seeing this as a 5 times a 2 for a 10, and then an x times an x times an x, 3 factors of x. And of course, with experience, you just get so quick with that, you don't even, you're not even aware of all the principles that are playing out in your head all at once. Now, a lot of people on the distributive rule, this is the second type of multiplication, write these little arrows that go into the parenthesis. And notice that when I do 2 times 5x, that's like this problem over here that I just did. And that becomes 10x. And then plus 2 times 1 is 2. You can do problems like 5 times 27 in your head if you see that the 27 is actually a 20 plus a 7, and you distribute the 5 into the 20, and you get 100. And you get a 5 into the 7, you get a 35. And in your head, you'd be able to see that as 100 plus 35, so 135. I'll do that a lot in class when we're working through problems in class. So just be aware of that. Then when I finally do this, x plus 3 times x plus 4, you can do that a couple of different ways. You can do it as repeated distributive rule, and this would give you an x squared plus a 4x, and then distribute the 3 across. That's literally what's happening by rule, which gives me now a 3x and a 12. And then I can simplify what's possible. The 4x plus 3x are like terms, so I can call that an x squared plus 7x plus a 12. So I have several options. We'll talk a lot about this form. This is kind of one of the central things of all algebra. Now, the last couple of principles are principles of reversing. So In addition, there's this thing called the additive identity, which is a 0. And if you add 0 to something, it won't change its value. 10 plus 0 is still 10. And if you, oh my goodness, this is a typo. A number added to its opposite. I'll have to fix that before I make that handout. A number plus its opposite is 0. So negative 5 plus 5 is 0. The multiplicative identity is 1. So if you multiply by 1, it won't change its value. So 10 times 1 is still 10. Any number multiplied by its reciprocal is 1. So if I had 4 times 1/4, that would be a 1. If I had 2/3 times 3/2, that would be a 1. And any number divided by itself, except for 0, would give a 1. 0 divided by 0 is an undefined mathematical expression. It's a nonsense expression. You're asking how many zeros does it take to make a 0? Well, it might take 1, it might take 1,000,000. So we don't know. That's why it's undefined. And then the inverse operations and functions. This is a key idea. Every forward step has a reverse step, an inverse step, an undo step. And if you apply both the forward and reverse steps, you get the original number. So suppose that I start with a 7 and I add 2, it becomes a 9. But what is the reverse step for an add 2? Well, it's a subtract 2. So if I take the 9 and subtract 2, I'm back to my original number. Suppose that I take 13 and I add 2, and the 13 becomes a 15. But what if I now take the 15 and reverse the process with the subtract 2? I'm back to the 13. So what happens is we'll have like an x, and we'll add 2 onto it, and it becomes an x plus 2. So what would happen if we took 2 away from x plus 2? Well, it would give us back the x. That's what you're doing in equation solving when you say x plus 2 is equal to whatever you want to say it's equal to. Just for fun, let's say it's equal to a 7. X plus 2 is equal to a 7. Then what you're actually doing is you're reversing the forward step of the add 2 by using a subtract 2. And the result of the add subtract gives us back the original x that we started with, and then we just do the arithmetic at the other side. So it'd be the same thing. 10 take away 5 would be a 5, but what would reverse a subtract 5 is an add 5, so 5 plus 5 gives me back the 10. I could say 7 take away 5 brings me to a 2, but if I add the 5 back on, I'm back to the 7. So if I saw x minus 5, if I started with x and subtracted 5, I'd have an x minus 5. But then if I added 5 back onto that, I'd have back the x. So what is it that reverses a times 3? So 5 times 3 is 15. What would get me from the 15 back to the 5? Well, the answer is divide by 3. And just to remember, divide by 3 is the same thing as times by 1/3. That's the division definition. So what if I had a 10 times a 3 to make a 30, and then I divided that 30 by the 3, that gives me back the 10. So what if I had an x times a 3, so x times a 3 becomes a 3x. What would I do to get back to the x? Well, I'd divide the 3 and I have back the x. Divide by 4, I could take, say, I'll make them easy. 12 divided by 4 is 3. And then what would reverse a divide by 4? Well, a times by 4. So 3 times 4 takes me back to the 12. How about a 20 divided by 4 is a 5, but a 5 times 4 takes me back to the 20. What if I see x divided by 4, and just to note, that could also be x times 1/4. Whoops, put that in the wrong place. What if I had an x and I divided it by 4? I could call that x divided by 4, or I could call it 1/4 x. So what would we get me back to the original x? Well, I'd simply times it by 4, and that would give me back the original x. The last thing that we have to remember is that whenever we're dealing with statements of equality, not necessarily equation, just statements of equality, whatever you do to one side has to be done to the other. So let's go back to first grade, and we had a we had an addition fact that said that 5 plus 2 is equal to 7. And there were two more related facts in that family. 7 take away 5 is 2, and 7 take away 2 is 5. So you're learning in first grade what they call fact families, just addition statements and the idea of combinations that create numbers, and seeing that subtraction is a form of addition. By the way, remember that's the definition. But algebraically, it would be like me taking 2 away from both sides of the equation. And if I did that, that would take me to this statement right here, that 7 take away 2 is 5. Or I could do it a different way, and I could say, let's take away 5 from both sides of this equation. And if I took away 5 from both sides of this equation, that would take me to this statement right here. So in one sense, those are just related facts, but in another sense, that's the principle of equation solving. Do the same thing to both sides of an equation. So these three principles here, 8, 9, and 10, go hand in hand when solving equations. So the principle number 8 was the idea of having reversing steps, and that when I reverse a step, it takes me back to the original, and whatever I do to one side of an equation, I have to do to another. These, along with principle number 2, the substitution idea, substitution, will govern this whole entire year. Understanding basically those, the associative properties, the commutative properties, distributive properties, they help in simplification. But understanding that this is the main things that we do in mathematics will really help this year for you. Good luck.